This one is 3.23 part F. Here we have a cantilevered beam which has this uniformly distributed load. In terms of reaction, at this point we are going to get a force reaction and a moment reaction. Now this uniform load can be replaced by a point load right at the middle, and the value of this force is going to be W naught L, and the distance from here is L by 2. So looking at this force system, this reaction right here is going to balance your W naught L. So this is W naught L, and the moment here is going to be minus W naught L square divided by 2, which will balance moment coming from this force right here. Now when we want to draw the shear force and bending moment diagram using singularity functions, we have a point moment here, point force here, and a distributed force here. So for the point moment, we will use the expression which is x minus a minus 2. For point force, we will use x minus a minus 1, and for distributed load or UDL, we will use x minus a power 0. And integration, minus 2 will become minus 1, and one more integration will give us power 0. Minus 1 0 here, and it becomes 1, and in this case one integration will be power 1, and second integration will be power 2 divided by 2. So for this, let's write the intensity function qx. So a qx in this case, we'll start from here. The first one is your point moment, so minus W naught L square divided by 2. Since it's a point moment starting at 0, so it's going to be minus 2 x minus 0. Then we have this point force going upwards, so positive direction, W naught L x minus 0 minus 1 because of point force. And then the distributed force, so minus W naught starting at 0, because of distributed force it's going to be 0. So I can integrate this to get the shear force Vx. So basically minus of q dx, this will give us the shear force. So we can flip the sign, and x minus 0 minus 2 will become minus 1. Again change the sign here, x minus 0 minus 1 will become 0, plus W naught x minus 0 power will become 1. Similarly, if you integrate this one more time from here to here with the negative sign, we can get the bending moment. So we have this x minus 0 minus 1 becomes 0 here, plus W naught L x minus 0 to the power 1 minus W naught x minus 0. This 1 will become power 2 divided by 2. So now we can evaluate these as polynomials. So if you look at your Vx, this one right here is an impulse function. So let's write this as impulse, which is at x equals to 0. And what does this mean? It means that the value of shear force at x equals to 0 is going to be infinity here. Just keep that in mind. This function right here, if you evaluate, this becomes minus W naught L x minus 0 to the power 1 is 1, plus W naught x minus 0 to the power 1 is going to be x. So I can simplify this to write W naught x minus L as a function, except for x equals to 0, and at x equals to 0 this value is infinity. Just keep that in mind. Similarly, if you evaluate your mbx, this function right here will give us minus W naught L square divided by 2, x minus 0 to the power will give you 1. From here we will get W naught L x minus 0 to the power 1 will give you x, minus W naught x minus 0 square will give you x square divided by 2. Now I can simplify this. If I take minus w naught by 2 common. Inside we get x minus L whole square. So basically we have got these two functions which we need to plot. So let me just draw an axis. So now this is an axis with the convention that we are following. So if I have to plot the shear force, this is a straight line which I can evaluate at 2 points, x equals to 0 and x equals to L. At x equals to 0 we get a value which is minus w naught L, and at x equals to L we get a value which is 0. So there is this negative value minus w naught L at x equals to 0 and 0 value at x equals to L. I can combine this by a straight line. So this is how your shear force looks for this beam. And remember, this point right here, this is a point where your shear force is going to be infinity. Now looking at your bending moment, this is a parabola which is opening downwards because the coefficient of x square is going to be negative here. And if you take the derivative of this also, it's going to give you x minus L, meaning the peak of this is going to be at x equals to L. So this is where the peak is going to be, and it's going to be opening downwards. And the value of this can be checked at 2 points, x equals to 0 and x equals to L. At 0 this value is going to be minus w naught L square by 2, and at x equals to L the value is going to be 0. So we can start from here to here, and since it's a parabola with peak at x equals to L, this is how the curve is going to be. So this is the bending moment diagram, and this value right here is minus w naught L square divided by 2. So that's how the shear force and bending moment diagram comes using singularity functions.